Hello everyone. Today we will talk about Hessian matrices in machine learning. Now you might be wondering, okay, what is this thing and why do we care about it in machine learning or optimization in general? Well, the Hessian matrix is a square matrix made up of second order partial derivatives. And what that really means is it tells us how a function curves or changes in different directions. If you are dealing with a function that depends on multiple variables like x and y, then the Hessian gives you a way to measure how that surface bends at any given point. So, in simple terms, it's like a curvature detector. It gives us more than just the slope. It tells us about the shape around a point. Not just whether we are going uphill or downhill, but whether we are sitting in a bowl, on a peak, or at a saddle. Alright, but why does this matter in machine learning? Well, let me switch. Sorry, okay. Uh, it turns out it matters quite a bit. When we are optimizing a loss function, I mean trying to minimize it, for example, we want to know where the local minima are. Optimization methods like Newton's method or LBFGS actually use the Hessian to guide their updates. They rely on second order information to move more efficiently toward a minimum compared to methods that just use the gradient. And another thing, understanding the shape of the loss function helps us avoid getting stuck at saddle points. These are points where the slope is zero, but it is not a minimum or maximum. The Hessian helps us detect these spots. Basically, it's a tool that gives us a better sense of the terrain, so to speak. Alright, so let me point something else out here, some key insights that come directly from looking at the Hessian. If the Hessian is positive definite, that means all its eigenvalues are positive. And what does that tell us? That we are at a local minimum. The function is curving upwards in all directions. So imagine you are in a bowl. Any direction you move, the value increases. If it is negative definite, so all the eigenvalues are negative. We are at a local maximum. The function is curving downward in all directions, like standing at the top of a hill. If the Hessian is indefinite, meaning it has both positive and negative eigenvalues, then we are at a saddle point. So in some directions the function increases and in others it decreases. Kind of like sitting on an actual horse saddle, okay? And lastly, the eigenvalues themselves, they give us more than just sign. They show us how strong the curvature is in each direction. So not just whether it curves up or down, but how sharply. And that's okay, I hope. Math part is here. Okay. So let's get a little more formal now. If we have got a multivariable function and let's say f of x1, x2 all the way to xn, then the Hessian matrix, which we usually write as capital H, is a matrix of second order partial derivatives. We can write that like this. H equals the matrix with entries partial squared f over partial x sub I partial x sub j sub prime. So basically every entry in this matrix is a second partial derivative with respect to two variables. That gives us a full second order behavior of the function, not just slopes but curvatures in every direction. Okay. Now let's make this more concrete with a two variable example. And suppose we have a function like this: f of x and y equals a times x squared plus b times xy plus c times y squared. That's written as like that, f of x, y equals ax squared plus bxy plus cy squared. Okay, so we have got a basic quadratic form in two variables. If we take the second order partials here, we can build a Hessian. The second derivative with respect to x twice gives us 2a. The mixed partial first with respect to x then y or y then x gives us b, and the second derivative with respect to y twice gives us 2c. So the Hessian matrix ends up looking like this, and H equals, and first row here 2a and b, and second row b and 2c. And notice something important here: it is symmetric. That is, the value in the upper right corner and the bottom left corner are the same. That's because the mixed partial derivatives are equal, assuming the function is smooth enough. Now let's talk about a few properties. Let me switch again, and okay. For symmetry, we just mentioned this, h sub I j equals h sub ji. That's due to the equality of mixed partials, which holds when the function is twice continuously differentiable. Then eigenvalues. One nice thing about the Hessian is that all its eigenvalues are real. You don't have to deal with imaginary numbers here, which keeps things simpler. And if all the eigenvalues are greater than 0, then the Hessian is called positive definite, and that means we are at a local minimum. If they are all less than 0, that's negative definite, and we are sitting on a local maximum. By the way, the assumption here is that our function is twice differentiable. That might sound technical, but what it really means is that all the second derivatives exist and they are continuous. This is a key requirement if we want to use second order optimization algorithms like Newton's method. Without that smoothness, the Hessian might not even exist or might not be useful. And okay, let's jump over to this little interactive tool and play with a real example. Okay, you can see. Okay, or coefficients here you can see. Okay, we are looking at a quadratic function defined as, what is that? F of fx y equals 1x squared plus 0xy plus 1y squared. So this is like this, f of x y equals 1 times x squared plus 0 times xy plus 1 times y squared. That's just a clean paraboloid. Okay, coefficient a is 1, b is 0, and c is 1. You can see, or let's make it okay. And so let's look at here. Based on those values, the Hessian becomes h equals 20002. Okay, and let's take a look at what this tells us. The eigenvalues are both 2.0. So lambda 1 is 2, lambda 2 is also 2. Okay, the determinant is 4, which is greater than 0, and both eigenvalues are positive. So we can classify this point as a local minimum. And if you think back to shape of the function, a ball opening upwards, that makes sense. Wherever you go from the origin, the function increases. Okay, that's what the positive eigenvalues and positive definitors are telling us. So the takeaway here is, once you have got the Hessian, you can tell not just whether you are at a flat spot, but what kind of flat spot it is. Is it a minimum, a maximum, a saddle? That all comes from the second order information, which is what the Hessian gives you. Okay, let's look at this. What's happening? Let me switch. Okay. So now let's talk a bit about how the Hessian actually shows up in practice, especially in machine learning workflows. And let's start with Newton's method. Look at this. So this method is a second order optimization algorithm, which means it uses both the gradient and the Hessian to figure out where to move next. The update rule looks like this. You can see x sub n plus 1 equals x sub n minus the inverse of h times the gradient of f. Basically, you take your current QS, subtract a correction term that involves the Hessian inverse multiplied by the gradient, and that gives you the next point. Okay, and that's okay, I hope. Now, what's nice about this method is that it converges faster than regular gradient descent, at least when the function behaves well near the minimum. But here's a catch. You have to compute the inverse of the Hessian, and that's not always cheap. Especially for high-dimensional problems, that inversion becomes a serious bottleneck. Okay, let's move on something closely related, analyzing the loss function. You can see here. When we train models, especially the fast to loss landscape can be pretty tricky. It's full of flat areas, steep cliffs, saddle points, all kinds of stuff. The Hessian helps us understand that terrain. It can show us where there are saddle points that might slow down training. It can help detect regions with sharp curvature where even small steps could overshoot. And that's useful when we are tuning the learning rate. Okay, and if the curvature is high, we want to take smaller steps. If it is shallow, we might be able to speed things up. So analyzing the Hessian gives us clues about how the model might behave during training and how stable that training will be. Okay, now there is another method you will see often in optimization, LBFGS algorithm. That stands for Limited Memory Broyden Fletcher Goldfarb Sharma, which is a mouthful, so we just say LBFGS. This is a quasi-Newton method, which means it approximates the inverse of the Hessian without actually computing it. That makes it way more practical for large problems. It needs less memory, which is why it is often used in neural network training, especially in settings where resources are limited or when the model is not too big. It is especially effective for convex problems where gradient descent can be slow to converge. Alright, speaking of neural networks, let's look at how second order information like the Hessian fits into that world. In deep learning, we don't usually use full second order methods during training because of the cost. But there are approaches like natural gradient descent that use curvature information in a more efficient way. These techniques can help with things like adjusting the learning rate dynamically, avoiding saddle points, and understanding the structure of the loss surface, which again ties back into stability and convergence. And okay, here let's pause for a second and look at some practical issues. And first up, the cost. Computing the full Hessian takes space that grows with n squared, and inverting it takes time that grows with n cubed. So if you have got a large model, it is just not going to scale well. That's why most real-world implementations rely on approximation like LBFGS, or sometimes just diagonal approximations where we only keep the second derivatives with respect to each variable. Another thing is stability. In some cases, the Hessian can be ill-conditioned. meaning it is close to being singular or unstable. That can mess with optimization, and in those cases we often need to regularize it to avoid numerical problems. And okay, let's look at this part. Let's work through a few example problems to see how the Hessian actually gets used in practice. Okay, and let's start with problem 1, just a basic Hessian computation. We are given a function f of x y equals x cubed plus 2xy squared minus y cubed. So f of x y equals x to the power 3 plus 2xy squared minus y to the power 3. First we will take the first partial derivatives, and to get this, that's the partial of f with respect to x comes out to 3x squared plus 2y squared, and here this is 4xy minus 3y squared. Now from there we go to second order partials. The second partial of f with respect to x twice is 6x. The mixed partial, first x then y, gives 4y, and same for other things, that's also 4y, and here is 4x minus 6y. So we can write the Hessian matrix like this. You can see h equals 6x 4y 4y and 4x minus 6y, and that's it. We have got our Hessian. The entries are all based on second derivatives we just calculated. Problem 2, critical point analysis. This time we are looking at critical points and classifying them using the Hessian. The function is f of x y equals x squared plus xy plus y squared minus 3x minus 3y. We start by taking the first order derivatives. You can see here partial is 2x plus y minus 3, and again partial here is x plus 2y minus 3. We set both equal to 0 and so, and that gives us x equals 1 and y equals 1, so the critical point is at 1.1. Okay, you can see here. Now the second derivative with respect to x twice is 2, and the mixed partial is 1 and other is also 2. You can see here. Then we calculate the eigenvalues. Here both eigenvalues turn out to be positive. Lambda 1 equals 3, lambda 2 equals 1. Okay, since both are positive, we classify the critical point as a local minimum, and it is located at 1.1. Okay, problem 3, ML application. What is that? Problem 3 is about deriving the Hessian for a common loss function. So we have got a quadratic loss. L of w equals 1/2 times, x w minus y transpose times. Okay, look at here, xw minus y, and L of w equals 1/2 times xw minus y transpose times xw minus y. If we expand it out, we get LW equal 1/2 w transpose x w minus y transpose x w plus 1/2 y transpose y, and taking the gradient, so the first derivative gives us x transpose xw minus x transpose y. Now we take the second derivative, the Hessian, and we get h equals x transpose times x. A few important things about this one. What are they? The first is the Hessian here is constant. It doesn't depend on w. So during optimization we are not recalculating it every time, which saves us some work. Also, if x has full column rank, then this Hessian is positive semi-definite. that's a good sign in terms of stability. And one more thing, in this setup, Newton's method gives the exact solution in just one step. That's one of the rare cases where it actually works out that neatly. Okay, but here's the catch. The conditional number of x transpose x affects the convergence. If it is poorly conditioned, you could uh, run into numerical issues or slower convergence even though the method is mathematically clean. And finally, if you want to explore this more, there are some good challenge problems here. They go beyond just theory, like implementing Newton's method yourself, comparing convergence rates, and testing how the conditional number of the Hessian affects stability. You could also try using LBFGS and comparing it against exact Newton steps. These kinds of exercises are really useful if you want to move from just knowing the definitions to actually understanding how to apply them. And that's for Hessian matrices. And thank you for listening.